A millisecond radio flash is pulsing every 16 days from 500 million light-years away. It is a repeating fast radio burst from another galaxy. Picture a lighthouse you cannot see, only hear. The beam is radio, not light, and it snaps on. Each burst lasts less than a blink, yet packs huge energy. The pattern repeats often enough to track, so yes, it is real, not noise. Bottom line, a distant object is ticking like a clock. Midnight at a quiet radio array, the sky hums with whispers. A fast radio burst is a millisecond flash of radio. This matters because it releases sun-scale energy in a blink. Magnetic monsters called magnetars fit the physics for many bursts. Their fields squeeze the crust until it cracks. The crack launches waves that whip charged particles to extreme speeds. Those particles radiate in a tight beam, like a laser in radio. Sometimes the engine resets, then does it again. That is how repeating bursts happen, without exploding the star. The typical energy per burst reaches about 10 to the power of 39 ergs. Durations can be 0.3 to 5 milliseconds, with sharp edges. Observers see polarization, which maps the magnetic dance during emission. That helps rule in or out different radiation processes. Example in real terms, one repeater fired thousands of times. It lives in a dwarf galaxy 3 billion light-years away. A faint persistent radio glow surrounds it like a hot nebula. The polarization spins as it passes magnetized plasma near the source. That tells us the environment is wild, with strong fields and dense gas. The data point to a young, restless magnetar in a star cradle. So the picture is, compact engines can flash again without dying. On a spectrogram, the burst sweeps downward like a slide whistle. Dispersion measure is the electron count along the path, measured by delay. It matters because extra electrons mean cosmic distance beyond our galaxy. Lower radio arrives later because plasma slows it more. Researchers compute our galaxy's share using electron maps. They subtract that from the total sweep they observe. The leftover is host galaxy plus intergalactic medium. Convert that leftover into a rough redshift with density models, then cross-check with follow-up telescopes and precise timing. For one repeater, the total measure was about 348 units. Our galaxy could explain only around 50 in that direction. The rest implies a source hundreds of millions of light-years away. Instruments like Chime catch many of these sweeps each day. They store raw voltages when something spikes above threshold. Teams replay the buffers, refine the delay curve, and stack bursts. The alignment proves a common origin, not random interference. Rule of thumb, smooth curves and consistent sky positions mean astrophysics. Net result, dispersion lets us tag a burst as extragalactic. Now the shocking part is the rhythm that keeps returning. An activity window means the source bursts only during certain days. That matters because a schedule hints at motion near the engine. A companion could blow a wind that blocks or allows the beam, or the magnetar itself could precess, wobbling like a spinning top. The wobble would point the beam toward us on a cycle. Plasma piles up and thins out, changing transparency with phase. Observers test this by folding the detection times on many trial periods. Peaks reveal a repeatable window hiding in the noise. One famous case shows a 16.35-day rhythm. Most bursts land within a 4-day slice of that cycle. The host is a pretty normal spiral galaxy, nearby by cosmic standards. It sits roughly 500 million light-years from us. In another case, the cadence stretches to about 157 days. The window lasts weeks, then goes quiet, then starts again. Telescopes schedule intense campaigns during the on-days to catch dozens. Bottom line, the clock-like behavior points to orbital or processing dynamics. Follow the beam through messy plasma, and the shape gets weird. Scattering is the blurring from many zigzag paths through electron clouds. This matters because geometry there encodes turbulence and distance to screens. The burst can grow a tail, decaying like a smudge after a spark. Polarized waves also twist as they cross magnetic fields. That twist depends on wavelength squared, revealing the rotation measure value. With both pieces, you diagnose density and magnetic strength near the source. Subbursts sometimes drift downward in frequency during one event. The slope gives clues to how the radiation is produced. In numbers, one repeater showed a rotation measure near 100,000. Over months, it dropped by about 10%, then leveled. That suggests a changing nebula or wind around the engine. Another repeater shows almost zero rotation measure, with crisp spikes. It probably lives in a cleaner region, far from tangled fields. Typical scattering tails range from microseconds to tens of milliseconds. In one band, the drift can be 200 megahertz per millisecond. What to remember: plasma fingerprints sketch the neighborhood around the source. Zoom into a host galaxy, and the neighborhood finally comes into focus. A host environment is the local place the engine inhabits. You care because birthplace reveals the engine's family and age. Young magnetars form after massive stars explode in bright supernovae. Those live in star-forming knots filled with blue, newborn giants. The debris can trap particles and pump magnetic fields to extremes. But another path lurks in ancient star clusters. There, compact objects meet in tight orbits after many gravitational dances. Collisions and accretion can spark bursts without young stars around. A standout case sits in the Milky Way group, only 12 million light-years away. Astronomers pinned it to a globular cluster packed with old red stars. Its bursts are weaker, between 10 to the power of 34 and 36 ergs. Some shots snap in microseconds, hinting at tiny emission regions. That contrasts with the energetic youth seen in star-forming dwarfs. 2 neighborhoods, 2 likely channels, 1 observable phenomenon. Net result: location tells you which engine likely drives the repeats. To name a street address, you need sharper eyes than a single dish. Interferometry combines many antennas to act like a giant telescope. It matters because bigger virtual size means finer angular resolution. Signals are recorded with atomic clock precision at each station. Later, computers correlate the streams, recovering delays between antennas. Those tiny delays map to a position on the sky. With baselines of thousands of kilometers, positions shrink to milliarcseconds. That is enough to land inside a single star-forming region. Observers often trigger this mode when a repeater wakes up. A string of bursts lets them refine the map rapidly. One team localized a repeater to within about 2 parsecs. It sat on a faint knot along a spiral arm in its host. Another was placed squarely inside a tiny, low-metallicity dwarf galaxy. The pinpoint then matches up with Hubble and ground images. Host type, star color, and even nearby nebulae become measurable. Bottom line: long baselines turn a sky blip into a street address. At the heart sits a city-sized star with a monstrous field. A magnetar is a neutron star with a magnetic field beyond belief. This matters because such stress can store and release colossal energy. Crust plates shift under magnetic pressure, like tectonics on overdrive. The snap launches Ulfane waves that race through the magnetosphere. Particles surf those waves and radiate coherently in radio. Shocks far from the star can also amplify radio emission. A companion star could orbit close, shedding a dense wind. That wind might gate the radio, creating days when we can see. Slow precession could sweep the beam across us on a cycle. These ideas are testable, using polarization, spectra, and timing statistics. The clincher came from our own galaxy in 2020. A known magnetar spat a radio flash with FRB-like strength. Detectors measured an energy near 10 to the power of 35 ergs. It rode along with an X-ray burst from the same object. That link shows magnetars can make at least some FRBs. So the takeaway is, natural engines fit the repeating story. That 16-day heartbeat from 500 million light-years now feels familiar. It is a repeating fast radio burst, likely from a magnetar. The schedule hints at a companion or a slow, graceful wobble. Dispersion, rotation, and scattering let us read the neighborhood in detail. Interferometers then drop a precise pin on the host. Together, the pattern turns a mystery ping into a physical system. If this kind of space sleuthing hooked you, stay for more. Tap subscribe and bring a friend who loves weird skies.